So similar to the Friedel-Crafts alkylation, the reaction of benzene with acyl chloride and the Lewis acid is called Friedel-Crafts acylation. And with the Friedel-Crafts acylation, a ketone group is introduced onto the benzene ring. So let's have a closer look on the reaction mechanism of Friedel-Crafts acylations. First of all, we start with the acyl chloride, which reacts with the Lewis acid, which is here aluminium trichloride. And in this first step, a coordination complex is generated, which will then, in a subsequent step, break down to form an acylium ion and tetrachloroaluminate. And here you can see the positively charged acylium ion is stabilized by resonance and a stronger electrophile than the acyl chloride. Hence, this acylium ion will react with benzene. In the third reaction step, benzene will then attack the electrophile, hence the acylium ion, to form a non-aromatic carbocation. And as we already saw in the previous slides, this carbocation is only one of the three possible resonance forms. Then in the next step, this non-aromatic carbocation gets deprotonated in order to form acyl benzene, as well as to regenerate the Lewis acid and to produce hydrochloric acid. Then, in the next step, the regenerated Lewis acid, the aluminium trichloride, reacts with the newly formed acyl benzene to form a coordination complex. And when the reaction is completed, water is added to the reaction mixture in order to induce the sixth step. And this last step is the hydrolysis of aluminium trichloride to aluminium hydroxide, and acyl benzene is released from the coordination complex, and additionally hydrochloric acid is formed. And important here is that in contrast to Friedel-Crafts alkylations, the Friedel-Crafts acylations only yield one product. So here we form acylium ions which do not rearrange, and the acyl benzene is less reactive to electrophilic substitutions than benzene, as it is a weaker nucleophile. The reason why the acyl benzene is a weaker nucleophile is that the acyl group has electron withdrawing effect. Hence, the product of a Friedel-Crafts acylation of benzene is only the unrearranged monoacylated benzene. Accordingly, Friedel-Crafts alkylations are more useful in synthetic reaction than Friedel-Crafts alkylations, as they do not yield mixtures of multiple alkylated benzenes. So for the formation of alkyl benzenes, usually Friedel-Crafts acylations are the first step, and then the produced acyl benzene can be converted with a reducing agent to convert the carbon-oxygen bond into a methylene group. And a common reaction to do so is the Clemmensen reduction. Here an acidic solution of zinc dissolved in mercury, which is also called zinc amalgam, is used, and the reduction takes place on the surface of the zinc. So let's have a closer look on what we can do. For example, if we start with benzene with this butanoyl chloride and we perform a Friedel-Crafts acylation reaction, we will end up with 1-phenylbutane 1-one as reaction product. And then we can continue with the just introduced Clemmensen reduction, where we have this zinc amalgam solution in order to reduce the carbonyl group to a methylene group, and we end up with this 1-butylbenzene molecule. And as already indicated, this Clemmensen reduction, so the reduction of this carbonyl group towards a methylene group, takes place on the surface of the zinc. So usually you do not directly use the Friedel-Crafts alkylation to produce monosubstituted alkyl benzenes, but you first do a Friedel-Crafts acylation followed by a Clemmensen reduction. And yeah, that's it for today. And for the next lecture, you can exercise the worked example 22.2, and you can do the end of chapter question exercise 2, A, B, and C. Furthermore, for the next lecture, please read already chapter 22.3 and 22.4, which can be found on pages 1027 until 1051.